survey and which kind of science we can do. So starting from the very beginning, what are accreting white dwarfs? These are compact interacting binaries in which you have a white dwarf, which is accreting from a companion star. This companion star, which is also called a donor because it's given mass, can be either a low mass missing star or even another white dwarf. And the donor star is in touch with its Roche lobe, therefore is losing matter through the inner Lagrangian point, and this matter is then accreted onto the white dwarf, typically with the formation of an accretion disk. And these binaries are compact, so their orbital periods span the range between few minutes up to 2 days. And also the orbital separation is comparable to the solar radius. So we cannot resolve these binaries, not even with Gaia. Okay, but why are they important? Why do we care about these binaries? So first of all, in accreting white dwarf, we can directly constrain all the key ingredients of the models of compact binary evolution. So because accreting white dwarf descends for at least one phase of common envelope, their evolution is driven by orbital angular momentum losses. And these orbital angular momentum losses continuously shrink the system, keep the donor in touch with its Roche lobe, set the mass accretion rate onto the white dwarf, and ensure the stability of the mass transfer process. And here, in a nutshell, you just have 2 plots to summarize how these binaries evolve. So the system is losing orbital angular momentum, so it's shrinking. So its orbital period decreases, and also the mass accretion rate onto the white dwarf decreases with the evolution. And the orbital periods and the mass accretion rates are 2 of the most important parameters that we can measure for accreting white dwarf, because then we can carry out direct comparison between the theoretical prediction and the observation. And actually, in accreting white dwarfs, we very often have access to both stellar components, so we can actually measure many other parameters. And we also have the potential to measure that for thousands of systems because they are relatively bright and nearby. So we have the possibility to carry out detailed population studies that we can use to constrain the key ingredients of the models describing the evolution of all types of compact binaries. And therefore, accreting white dwarf are the best laboratory that we have to test, develop, and constrain our understanding of the mass transfer process and binary evolution. And accreting white dwarf are also connected to supernova type Ia. I'm not going into the details of the different scenarios because which configuration can actually lead to a successful explosion is still under debate. The double detonation scenario seems to be quite promising, but this is outside of the topic of this talk. This is just to highlight that understanding the formation, evolution, and final fate of accreting white dwarf is important because then we also get to understand the path towards supernova type Ia explosions. Okay, so we want to study accreting white dwarfs. How do we find them? So accreting white dwarf are mainly discovered thanks to their variability. So this is the first accreting white dwarf that was discovered in 1855, is Euge Minorum, and you can see that it undergoes this bright outburst every about 3 months. These outbursts last between days, sometimes a week, and during this outburst, the system brightened from 14 up to 9. So you have a 5 magnitude jump. And these outbursts are called dwarf nova phenomenon and are related to thermal instabilities in the accretion disk. So the accretion disk becomes thermally unstable. You have an increase in viscosity in temperature. This makes your disk bright, and that's why you get this large amplitude variation. And in accreting white dwarf, we typically observe outbursts with amplitude between 2 up even to 9 magnitudes. So we mostly find accreting white dwarf thanks to this behavior. There are also different types of, this pointer is not working, these other types of variability that are discussed in different posters. So I'm not going to go in details. I just point you to these talks. And then, so we can find accreting white dwarf from their variability. X-rays is also a very useful waveband, and in the X-rays, we are more sensitive to magnetic system containing magnetic white dwarfs. Accreting white dwarf can also be found thanks to their blue colors, and the colors of accreting white dwarfs also overlap with those of quasars, and therefore Sloan has been quite important because accreting white dwarf have been a byproduct of Sloan, which allowed us to confirm about 500 accreting white dwarf with their spectra. And here you can see the discovery rate of these binaries. This is a plot that I stole from Madrid and shows the number of systems discovered with time. And you can see since the discovery, there was an increase. And then you can see when Sloan comes online, and then you can see the big jump with all the transient survey, with CRTS, ZTF, and Gaia making the big part. And Elma is going to tell us about Gaia on Thursday. So the current state of the art is that we have about 10,000 systems, including confirmed accreting white dwarfs and also candidate, where a candidate is everything that has shown some kind of variability resembling that of accreting white dwarf, but for which we don't have, for example, a period determination or a spectra that can confirm that this is a genuine accreting white dwarf. For more than 1,000, we have orbital periods, which again is important because it gives us an idea about the evolutionary state. And only a small fraction of them has been characterized with masses and temperature. And so far, we have been able to build one volume limited sample of object out to 150 parsec, but you can, thanks to Gaia. And you can see we have only 42 objects in this sample. So it's also, while we could carry out the first study, population study of accreting white dwarf, it's also difficult to understand what's the role played by a small number statistics within this sample. So this is the state of the art with the limitation, and LSST is going to be a big revolution in the field. So in order to compute that, I took this simulation from a paper by Fantin et al., where they show the number of single white dwarfs as a function of the observed magnitude. And you can see here in green, there is Gaia that stops at magnitude 20, and then you have LSST going to 24.5 in a single visit, down to 27 by the end of the entire survey. Since we know the relative number between white dwarf and accreting white dwarf, we can estimate that in the single visit, with survey down to 24.5 magnitude, we will expect to find 60,000 accreting white dwarfs. And by the end of the survey, we will have 160,000 systems. And the big impact of this number is that actually with LSST, we will be able to probe much larger volume that are accessible at the moment. So here you have the observed magnitude as a function of the distance. And in this band, which should appear gray, but it doesn't matter, here you have how the accreting white dwarf will look like with the distance. So your lower limit is set by the system accreting at the lowest rate, because the accretion rate sets how bright is your system. So with Gaia, which stops at magnitude 20, we will be able to sample down out to 400 parsec. And then you can see that basically we are limited. It's with Gaia, we will not be able to build volume that are complete beyond this distance, because we will be missing the faint end of the population, which actually represented the bulk. With LSST instead, we will be able to explore out to 3 kiloparsec. And this will allow us to build volume limited sample of object for which we can study the properties of the population. Okay, so what's important now is that with LSST we can do that, and we already have all the tools that are necessary to identify accreting white dwarf in LSST. So we already have different machine learning techniques that have been developed for ZTF and the Gaia alerts that can be applied to the LSST photometry in order to find accreting white dwarf from the dwarf nova outbursts. We have different variability metrics that have been developed to identify variable white dwarfs. So the idea behind this metric is that you take the photometry and you look at the uncertainties after you average over several visits. Single white dwarf, they shouldn't be variable. So the uncertainties on their magnitude should be small. So if you compare the magnitude of an object with that of a nearby object with comparable magnitude, and you find something with a large uncertainties, this is a clue of variability. And this method, which have been developed for white dwarf have actually turned out to be quite successful in identifying low mass accreting white dwarfs, which are the most difficult to find because they outburst very rarely, so they are the least variables, but with this metric we are sensitive to them. Also, with LSST, we will have colors and proper motion. And there is this method developed by Gentile Fusillo et al. In 2015, developed on the SDSS data, where you can basically identify white dwarf combining their colors and their proper motions. And this method is quite nice because you also get the probability of the object to be a white dwarf. So once you know the probability, you also can basically build up a ranking of the object that you want to follow up first. So you get relative importance of the thing that you want to observe. And finally, we will also get parallaxes with LSST. And this is important because accreting white dwarf are mainly found between the main sequence and the white dwarf track. So we can also do a selection using their position in the HR diagram. Okay, so we have LSST, we have the data, we have all the tools to identify accreting white dwarf. What do we do with that? Well, we want to carry out population studies, so we want a sample that is as complete and as pure as possible. With all those methods that I showed you, we will identify accreting white dwarfs, but a lot of accreting white dwarf candidates. So we will have also lots of contaminants. So we need to be able to clean the sample, and to do that, we need identification spectra. So here you have some X-shooter spectra for different types of accreting white dwarfs, so you have an idea of how they look like. On the top panel, you have spectra in which the disk is dominating the emission of the system. So they are accreting a relatively high accretion rate, and you can recognize the disk from these strong emission lines and this blue continuum. When you go to lower mass accretion rate, then you start to see the donor in the near infrared, and you can even see the white dwarf here with this Balmer absorption feature. So there are different instruments at ESO that can already be used for this kind of observation. You can use EFOSC for the brightest one. SOX and X-shooter will be very nice because then you can get the entire spectral energy distribution and you can observe the white dwarf, the accretion disk, and the donor in one shot. Force is going to be useful for the faintest one. Cubes has the possibility to be helpful. But I put it in bracket because its wavelength range will stop here. So we will get the Balmer jump, but no more than that. But of course, we are talking about thousands of objects, so we can't just follow up them one by one. We need a more efficient method. And the game changer will be, of course, Foremost. Foremost, we already heard, is a multi-object spectrograph on the VISTA telescope. We'll be able to obtain spectra for 2.5 thousand objects in one shot. And within Foremost, we have the white dwarf binary survey, which is led by Odette Tolosa and Alberto Rabassa Mansergas. And the aim of the survey is to obtain spectra of all white dwarf in binaries, so including white dwarf in non-interacting binaries, which are about 150,000 objects, down to a magnitude of 20. And this survey will include also thousands of accreting white dwarf. So Foremost is going to be very helpful, but again, Foremost can't go beyond magnitude 20. If we want to go fainter, then we need hopefully to have WST available, that with its aperture of 12 meters, will be able to obtain spectra down to a magnitude of 23. So I'm not going to talk about WST because we will hear about it from Richard on Thursday. I just want to mention that within the Galactic Working Group, we have submitted a science case with the aim to observe all white dwarf in binaries in this magnitude range. Okay, so basically we have all the tools to build samples, complete samples of accreting white dwarf. What are we going to do with those? What is the science that we can do? So we definitely want to carry out population studies. And with volume that are complete and as pure as possible, we can derive the space density. We can constrain our space density much better than done with the 150 parsec sample. We can derive the period distribution. And the period distribution is important because accreting white dwarf evolved from long towards shorter orbital period. So the fraction of a system at long and short orbital period will basically tell us the evolutionary timescales, which reflects the mechanism of angular momentum loss driving the evolution of these systems. And also, we will be able to look at the distribution of accreting white dwarf in our galaxy. And this is important because at the moment, we haven't been able to measure the scale height of the population. And at the moment, we can't because some of the system the faintest one, the oldest one, have a scale height which is estimated at least of 450 parsec. But, sorry, 400, yes, 450 parsec. But with Gaia, we can go as far as 400. So with LSST, we will be able to explore larger volume, obtain constraint on the scale height of the population, which tell us about the age, and the age, again, constrain the evolutionary timescales, which reflects the angular momentum loss rate in the system. And we can use that to constrain the model of compact binary evolution. Also, we will not find only accreting white dwarfs, but we'll also find their detached progenitors. And once we compare the space density of the two populations, we also get constraint on the efficiency of the common envelope phase. And this is important because common envelope phase is a phase that enters in the evolution of all compact binaries, but at the moment is still poorly constrained. With accreting white dwarf, we can also put constraint on the efficiency of this phase. And something that is more recent is this work by Scaringi et al., which has shown that accreting white dwarf will contribute to the foreground signal arising from unresolved binary in the galaxy. And this unresolved signal, this signal from unresolved binary will basically limit the sensitivity of LISA in detecting gravitational waves. In this paper is explained how this bump is related to the space density of accreting white dwarf. So with population studies, we will also be able to constrain this bump and understand how the population of accreting white dwarf will affect the sensitivity of LISA. And finally, just want to mention that we will also have the opportunity to characterize single system. This can be done with spectroscopic fit. So here you have an example of an X-shooter spectrum. And you can see that in red is the best fitting model that is composed of the sum of a white dwarf synthetic model here in blue with this Balmer absorption feature, an accretion disk with these strong emission lines, and the donor in the near infrared. With this kind of study, we can measure the parameters of the system. We can get masses, temperature, accretion rate, rotation rates, and these are all parameters that, again, allow us to carry out a direct comparison between the observation and the prediction of the theoretical models. And in this way, we will also be able to look for accreting white dwarf with brown dwarf donors. And these are particularly important because the theory predicts that the majority of accreting white dwarf should have evolved and the donor star should have lost such big amount of mass that it turned into a brown dwarf. And this should make up for 80% of the population. However, in the 150 parsec, we find a much smaller fraction, between 7 and 14%. So what's going on in here? Is this an effect of small number statistics? Or this binary do not exist? And if they do not exist, what's the reason there? Is because we do not understand the response of the donor to the mass loss process? Well, looking at this large sample, being able to go faint because the systems are expected to be intrinsically faint, we will have the opportunity also to test this theory and understand how donor star responds to the mass loss process, which again is important for all mass exchanging binaries. And this is my last slide, just to summarize. LSST will come online soon. We have all the tools to efficiently mine the database. So we have all the tools to find accreting white dwarf. Well, ESO will provide us all the facilities that we need for an efficient follow-up of these targets. And we will be able to carry out detailed population studies for which we can constrain the evolution of compact binaries, the emission of gravitational waves, and also the path towards supernova type Ia explosion. Yes, there is a lot of science that can be done with accreting white dwarf, with single white dwarf. I couldn't include everything in 20 minutes, but I'm very happy to talk about it. So please come and look for me during coffee break if you want to talk about that. And thanks for listening to the last talk of the session.
told you it's not going to be a good one. Go ahead.
Thank you for the talk.